In the last lecture, I discussed about the amplitude ratio and phi of individual components, as well as I told you that how you can find the AR and phi of a transfer function which you can make by multiplying the individual transfer functions, right? So what you have to do, make a table, right? On that table, mention all those 7 components, the basic components, right? Because once you know the AR and phi of those basic components, then you can always calculate the AR and phi of overall transfer function. Please note that while calculating AR, while calculating phi, we only require open transfer functions. It is very, very important. While calculating AR and phi, we only require open transfer functions. However, when we were calculating that, when we were solving the stability problem by Routh stability criteria, we used closed loop transfer function. Its denominator, which was 1 plus open loop transfer function, which equal to 0, becomes the characteristic equation. So you have to be careful. ये छोटी गलतियां होती हैं many times. The question is given you the open transfer function or closed loop transfer function. You have to be careful while reading these things. Okay. So just make the table and write all those 7 basic components. Please note that I told you a short method that put S is equal to iota omega. Once you put S is equal to iota omega, then you can just write down that in the form of a standard complex number and then find the modulus, find the argument. Modulus becomes equal to amplitude ratio. Argument becomes equal to this, argument was equal to the phase angle of the system, right? But when you have overall transfer function, which is made by multiplication or division of these individual transfer function, in overall transfer function, don't put S is equal to iota omega. In fact, break that overall transfer function into individual so that you know the AR and phi of each individual. And then use the property. I told you 2 property, that AR of overall is equal to the multiplication of individual transfer function and phi of overall is equal to the sum of individual phi. Right? अगर आप इतना कर लेते हैं, then you are done with the calculation of AR and phi. Because I told you about all the basics. Okay. Now we were doing the frequency response analysis. In the frequency response analysis, we were actually doing stability analysis. In stability analysis, frequency response analysis. In this, I discussed about AR and phi. Now you know what is AR, what is phi. Correct? Now there comes a very special topic which is called Bode plots. Why special? Special because during semesters, I don't think that even a single student is able to understand that how these Bode plots are made. Even when I was in my pre-final year, we were having these subjects of process dynamics and control. It was in 2 parts, process control and advanced process control in some other semester. I was able to understand advanced process control. I scored very good in advanced process control. I think the paper was quite easy. But when you talk about this basic process control and this particularly this Bode plots, I had no clue that how these plots are being made. And by chance, that semester exam paper was, I mean, it was not prepared by our faculties of the university. It came from somewhere else. I don't know. People said that it is coming from IIT Delhi. I don't know. This may be the rumor, or I don't know. Whatever happened, I had no clue what to write in the paper regarding this Bode plot. I mean, it was the most difficult kind of question for me. And I tried a lot and I was just able to score passing marks. So, Bode plot कभी students को बीटेक में ज़्यादातर cases में नहीं समझ आता. समझाते भी नहीं, समझाने वाले भी इसको नहीं समझाते हैं. In GATE exam, this Bode plots, hardly we will be dealing with 1.5 or 2 hours and the Bode plots is done. Okay, even I don't know how much time it would take. Okay, so but not more than 2 hours. Okay, so and why these Bode plots are required? Because ultimately I told you that why we are doing these things. After these Bode plots, there will be discussion of Bode stability criteria. Now, Bode stability criteria is based on AR and phi, just like Routh stability criteria. Routh stability criteria was based on this characteristic equation. Bode stability criteria is based on AR and phi and the Bode plots. Fine. Actually, Bode stability criteria is based on Bode plots. And Bode plots are based on AR and phi. So, I told you that discuss first AR and phi. Now, Bode plots, then Bode stability criteria. So, what are Bode plots? And when I say plots, it means plural, right? So, write down, these are, or Bode plots are 2 plots. Simultaneously, we call them Bode plots. set of two plots. Both of them are called Bode plots. Okay. The first plot is between AR, amplitude ratio, or MR. Now, what is MR? MR is called magnitude ratio. What is magnitude ratio? I will discuss. So, the first plot is between AR or MR and omega or omega tau, right? See, you have seen that when we discussed AR, amplitude ratio, and phi, all the cases AR was a function of omega somehow. Otherwise, AR was constant or it was a function of omega. Similarly, phi, either it was constant or it was a function of omega. So, of course, I can make a plot between AR and omega, right? So, the first plot is between AR and omega, AR or MR, and omega or omega tau. I mean, it can be anything, AR versus omega tau, MR versus omega tau. MR is known as magnitude ratio, okay? On a log axis. और यहीं पे सारी प्रॉब्लम आ जाती है that we are not very much comfortable with the logarithmic axis. Actually, it's not difficult, but we are not habitual of using logarithmic axis. We are habitual of using Cartesian axis, where if this distance is 1 unit, then this distance is 1 unit, then this distance is 1 unit. This is called Cartesian axis. 1, 2, 3, equal distance, equal numerical values, equal gaps. This is the feature of Cartesian axis. We normally work, agar aap dekh lo, from your school time to when you completed your bachelor's, most of the time we have never seen logarithmic graphs. I had never seen logarithmic graphs. Okay, what is a log plot? I had no clue, I had no idea even when I completed BTech. I should have idea even when you have when you are completed BTech, and suppose you don't know what is log plot, you should know actually. Okay, but we don't have no, in most of these subjects it is not required to develop the understanding of log plot. Similarly, there are other plots like semi-log plots. Similarly, there are other plots like triangular plots. Now, what are triangular plots? In extraction diagram, you can get a triangular graph paper. That graph will be used to solve the extraction problem graphically. So, we normally don't have a habit. We are not very much comfortable with these different kind of graphs. We have a habit of Cartesian graph, not log graph. I will discuss what is the difference, but first write the definition that the first plot is between AR or MR and omega or omega tau on a log axis. Log axis means X and Y, both axes are logarithmic axis. The second plot is between phi and omega or omega tau, right, on a semi-log axis. These two plots are called Bode plots. First of all, I'm plotting AR versus omega and phi versus omega. You know that AR is a function of omega, phi is a function of omega, so definitely I can make a graph. But the question arises, what is this log and semi-log, and what is this Cartesian? You must have seen that in a Cartesian coordinates, first of all, what is log axis? You can make here. Log axis means, or log axis se pehle chodo, what is the meaning of logarithmic coordinates? Wo samajhta, then I'll come to log axis and semi-log axis. See, we have Cartesian coordinates, suppose. We all are, I mean, hum sochte bhi nahi hai what is the meaning of Cartesian coordinates, because from the very starting, from the primary schools, we are dealing with this Cartesian coordinates. So we feel like this coordinate system is one of ours, and we don't have a feeling of, this foreign kind of material for this Cartesian coordinate. But जैसे ही आपको log coordinate या semi log की बात करते हैं, you have a fear inside you that what is this? We have never dealt with this log coordinates. Okay, Cartesian coordinates means, suppose this is the Cartesian coordinate. If this is 0 and I'm taking a fixed distance, this is 1. Again the fixed distance, this is 2. Again fixed distance, this is 3, 4, 5. कार्टेशियन कोऑर्डिनेट का मतलब ये होता है कि बराबर दूरी लोगे आप, you take equal distances and therefore there will be equal increments in the numbers also. That is the meaning of Cartesian coordinates. See, we know that y is equal to mx plus c is the equation of a straight line, correct? This is Cartesian coordinate. Equal distance, equal increment, correct? That is the feature of Cartesian coordinate. लिख लो इसको. In Cartesian coordinates we have equal distance, है ना, and equal distance causes equal increment, है ना, 2 to 3, 3 to 4 equal increment, correct? You know that y is equal to mx plus c is the equation of a straight line. X square plus y square is equal to r square is the equation of a circle having radius r. Similarly, there are other equations for parabola. Y equal to 1 by x is for hyperbola. Y is equal to x square is kind of parabola with whose mouth is open upwards. Y square is equal to 4x is the parabola whose mouth is open towards the positive side of x-axis. Like this, we have learned a number of equations, 15, 20 equations. So, y is equal to mx plus c is the equation of a straight line. Y is equal to 1 by x is the equation of a rectangular hyperbola. But all these things we have learned with respect to what? आप बचपन से सारी चीजें पढ़ते आए हो with respect to what? With respect to Cartesian coordinate. Means y is equal to mx plus c. Y is equal to mx plus c is the equation of a straight line, right? Equation of straight line, correct? But on which coordinate? Only on Cartesian coordinate. Only on Cartesian coordinate. Similarly, y is equal to, I'm just taking one or two examples, there are many more, is the equation of, you must have studied, na? Xy is equal to constant is the equation of a rectangular hyperbola. Equation of rectangular hyperbola. ठीक है? Equation of rectangular hyperbola, but only on Cartesian axis. So ये ध्यान रखो कि आपने पढ़ तो लिया कि नहीं सर ये तो हमेशा इसी की इक्वेशन होती है. Why? Because you most of the time deal with the Cartesian axis only. So आपने कभी सोचा ही नहीं कि what will be the form of this equation on a different axis, right? So now I have logarithmic axis. What is the meaning of logarithmic axis? Let's see. Logarithmic axis is different from Cartesian axis. How? Logarithmic axis. Here, suppose I am talking about log to the base 10. I am talking about log to the base 10. Correct? आपको log की properties तो पता ना, basic properties I hope इतने सभी को पता होंगी. This point is 10 raised to the power, let's say minus 2. Fine. I am taking equal distances. आप बोलोगे सर distances तो यहाँ पे भी equal थे. Yes, here also I am taking equal distances. Seems like equal distance. Yes. It seems like, yeah, distances are equal. ठीक है? If it seems like they are not equal, please draw it again. Now they are equal, okay? Equal distances. If this is 10 raised to the power minus 2, why 10? Because I am dealing with log to the base 10. Then this one is 10 raised to the power minus 1. This is 10 raised to the power 0. This is 10 raised to the power 1. This is 10 raised to the power 2, 10 raised to the power 3, and so on. This is called logarithmic axis. Now see yourself. Here, equal distance has equal increments. 1 minus 0, 2 minus 1, 3 minus 2, 4 minus 3, 5 minus 4. Everything is 1. Here, distances are equal. But what is this? 0.1. This is 0.01. 1, 0.1. 10, 1. 1, 10, 100, 1000. What do you see here? The ratios are equal. However, if you talk about the differences, this is 1000 minus 100, which is 900, and this is 100 minus 10, which is 90. This is 10 minus 1, which is 9. So the differences are not same, right? The differences are not same. I can also make this in a slightly different way, that suppose this value is 1, 10 to the power 0 is 1, and this is 10. Fine. So if you ask me that, sir, if you see what I have done here, I have taken equal distances. I have taken equal distances, correct? but the gaps, the increments are not equal. But suppose if you take equal increments on the logarithmic axis, आपने कहा कि सर ये 1 है और ये 2 है और मुझे 3 लेना है, then 3 will be something like this. 4, 5 keeps on decreasing. The gap keeps on decreasing. Let me make this again. So 1, suppose this is 2. I want to plot 3. Then this will be 3. 4. The gap keeps on decreasing. 5, 6, and so on. So you'll find that there will be somewhere 10, 7, 8, 9, 10. This is 10. So on the logarithmic axis, this is the scenario I have. This is 10 raised to the power 0. I'm trying to make this 10 raised to the power 1. And then again, it will be, suppose I'm taking the same distance. Let me make a bigger one here for your understanding. This is 10 raised to the power 0, 10 raised to the power 1, 10 raised to the power 2. Correct? This is how you can understand the logarithmic axis. This is how, see, this gap is equal, but the difference, this is 10 and this is 1. So difference is 9. However, here the difference is 90. The ratios are same. But suppose if you want to ask me, sir, yeah, this is 1, where is 2? So this is 2, right? So this is how 1, 2, 3, you can see that if I take equal increments, the gaps are decreasing. This is the logarithmic axis, right? This is logarithmic axis. Okay, if it is the base 10, it can be base 2 also, it can be base e also, right? It can be base e as well. Okay, so this is the difference between coordinate axis and logarithmic axis. Now the thing is, suppose one more thing I would like to mention here. What is the conclusion of all these things? Conclusions of difference between Cartesian axis and logarithmic axis. देखो, एक conclusion ये समझना है that whenever you plot a particular equation on coordinate axis, it is giving you some kind of shape for circle, straight line. But if you plot the same equation on this logarithmic axis, the shape is going to change. पहले ये समझना चाहिए that the equation will not look same on Cartesian and logarithmic axis. Equation is same, but the shape which it is giving, right? You know that y is equal to mx plus c. If you plot it on this Cartesian coordinate system, it is going to give you a straight line. But if you plot y is equal to mx plus c on the same this logarithmic system, logarithmic coordinate system, it will be something else. So first point, the shape or a curve, you can say, है ना, plot, है ना, of an equation, the same equation on Cartesian coordinate, and on logarithmic coordinates will be different. Cartesian coordinates and on logarithmic coordinates will be different. है ना? तो ये नहीं समझना कि y is equal to mx plus c is always the equation of a straight line. You plot it on the logarithmic plot, it will be giving you something else. Okay, one more thing. Achha, it can be log 10 also, it can be log e also, है ना? It's not always log 10, it can be e also, then e raised to power minus 2, e raised to power minus 1, e raised to power 0, like that. Okay, secondly, suppose I want to locate log 2 on Cartesian coordinate. How you are going to do that? Suppose I ask you a question ki, do one thing, Mr. Suresh, take Cartesian coordinate, and this is the Cartesian coordinate. Suppose this is 0, this is 0.2. I'm just taking small gaps for ease. 0.4, 0.6, 0.8, 1. Right? Suppose this is my Cartesian coordinate. It is Cartesian coordinate, equal gaps, equal intervals. Okay. Now, if you try to find the value of log of 2, log 2 I want to find. Okay. Now, the question is, okay, log 2, let's see. What is the value of log 2? 0.693 if you are taking the log to the base e, and it is 0.301 if you're taking, so I'm taking log to the base e, not a problem. Okay, log to the base e. Log 2 is coming out to be 0.693. Suppose this is log, I have to find log 2. You know that log 2 is equal to 0.693. You have to remember this value as well. I want to locate log 2. How I'm going to locate log 2 on this Cartesian axis? I'm first going to find that, okay, the log 2 is coming out to be 0.693. You know that log 2 is coming out to be 0.693. So first of all, what I'm going to do, I will calculate log 2 and then I will plot here. Where is 0.693? Somewhere around 0.7. So this should be log 2 on this axis. Fine. Similarly, suppose I want to plot log 3. I am saying that plot log 3. What is the value of log 3? Log 3 is, okay, log 3 is coming out to be 1.09. Huh? Okay. Okay, let us calculate to the base e, not a problem. इसको 10 के बेस पे कर लेते हैं, because otherwise मुझे ग्राफ बड़ा करना पड़ेगा और कोई प्रॉब्लम नहीं है ना. Log 2 is coming out to be 0.3010. We used to remember all these values in our high school, but अभी आप ln2 की याद रख लो, वो भी बहुत है ना. Log 2 is 0.3010 and what is log 3? This is log 3 is 0.4771 है ना. Suppose I ask you that plot log 2 and plot log 3. This is also to the base 10. On this Cartesian systems, first of all, what you are going to do, you will calculate log 2 and log 3. That log 2 is equal to 0.30. So this value is equal to log 2 and log 3 is equal to 0.47. So somewhere here, this value is equal to log 3. So I plotted log 3 and log 2. Correct? This is how you plot log 3 and log 2 on the Cartesian coordinate. Now the question is, suppose we have to plot log 2 and log 3 on logarithmic axis. Locate log 2 to the base 10 and log 3 to the base 10 on logarithmic axis. Now you will see that how I am going to do this log 3 on logarithmic axis. Okay? Locate log 2 and log 3 on logarithmic axis. So first of all, let us make the axis. Okay, suppose this is 10 raised to the power 0, which is 1. Then we have 2. This is not 10 raised to the power 2, this is 2. Okay, then we have somewhere we have 3, 4, 5, right? 6, 7, 8. The gap is decreasing, right? Even if it does not seem that it is decreasing, please assume that it is decreasing. This is 10 and then it is 10 raised to power 2. This is how. Okay, now suppose I want to plot, I want to locate where is log 2. So log 2, अब आपको यहाँ पे log लेने की जरूरत नहीं है. Don't find log 2 here. When you are locating log 2 on the logarithmic axis, this is what is the difference. Here, you have to first calculate log 2 and then plot that value on the Cartesian axis. यहाँ पे अगर आपको log 2 plot करना है, then just don't worry about the value of log 2. Just plot log 2 is equal to this. Right? This value, log 2, becomes 2 on the logarithmic axis. This is important that this is log 2. And what is log 3? This is log 2. And where is log 3? Log 3 on the logarithmic axis becomes 3. ये बहुत इंपॉर्टेंट समझना है. देखो ऑन लॉगरिथमिक एक्सिस आपको लॉग लेने की जरूरत नहीं है, ऑलरेडी लॉग ले रखा है. ये इस एक्सिस में लॉग का इफेक्ट है. द लॉगरिथमिक एक्सिस इन इटसेल्फ कंसिस्ट ऑफ द इफेक्ट ऑफ लॉगरिथम. सो नो नीड टू टेक लॉगरिथम and check the value and then plot it. No, log 2 on the log axis becomes 2 and log 3 on the log axis becomes 3. This is log 2, this is log 3. This is how you locate log on log axis on logarithmic coordinates. Suppose I want to locate that, try to locate log 3 minus log 2. How to find this? Log 3 minus log 2. On the Cartesian axis, this value will be log 3 minus log 2. This difference will be log 3 minus log 2, है ना? This difference will be log 3 minus log 2. What about here? What is log 3 minus log 2? Can I write log 3 minus log 2 as log of 3 by 2? Can I write like this? Here also you can write. Here also you can write log of 3 by 2, and then log of 3 by 2 you can calculate what is log of 3 by 2, and then you are going to plot it. You can do that if you want to find log 3 by 2, log 3 minus log 2 here. So what about this one? Log 3 minus log 2 becomes log 3 by 2, and log 3 by 2 on the logarithmic scale, how you are going to plot it, becomes 3 by 2. Where is 3 by 2? 1.5 somewhere, so it is somewhere here. Log 3 minus log 2. So log of 3 by 2 becomes 3 by 2 on the log axis, right? So please remember, log 3 by 2, where is 3 by 2? Log 3 by 2, this is 1, this is 2, somewhere here 1.5. This is log of 3 by 2, and this value is nothing but log 3 minus log 2 on the log axis. However, here you will write log 3 minus log 2, okay, and then you will find log of 3 by 2, you will calculate the value and then locate on this Cartesian coordinate system. So what is the second conclusion? The second conclusion is, on the Cartesian coordinate system, you have to calculate log first and then locate it. While in the logarithmic axis, on the logarithmic axis, already the effect of log is present on the axis, and no need to calculate log. Log 3 becomes 3, log 4 becomes 4, log 3 by 2 becomes 3 by 2, log 1 becomes 1. Log 1 is not 0 on log axis. Very important conclusion. That is why you are not able to understand the Bode plot. Log 1 on logarithmic coordinates becomes 1, not 0. Here if I ask you that locate log 1, you'll say that, sir, this is log 1. Why? Because first of all, you'll have to calculate log 1. Log 1 is coming out to be 0, and 0 is present here. But locate log 1, this is log 1. Right? So 10 raised to the power 0, log 1. Right? So log 1 becomes 1 on the Cartesian axis. And log 10 becomes 10 on the Cartesian axis. Log 100 becomes 100 on the Cartesian axis. On the logarithmic axis, I'm sorry, I think I said Cartesian axis. So in the logarithmic axis, the effect of log is already incorporated. So आपको log लेना नहीं है, and that is why log 1 remains 1 here. Right? That was the second conclusion. Now the question is, third conclusion is, what is the meaning of log and semi-log axis? Log axis and semi-log axis. First of all, you please understand this. आगे काम आएगा that suppose y equal to e raised to the power x. You know what is the nature of the curve? Y equal to the curve is this. आपसे बोलूँगा sir please plot. आपको मैं बोलूँगा please plot the graph of e raised to the power x. You will not give a second thought and you will already make this. But this is only for Cartesian axis. If you plot y is equal to e raised to the power x on logarithmic axis, then think about it. It will not remain this. So that's why I am saying here that the nature of graph of an equation changes when you plot it on the logarithmic axis instead of Cartesian axis. So when I talk about log axis, it means both y-axis and x-axis are like this. This is also log axis and this is also log axis. This kind of equation is called log plot. Semi-log axis, this is also log axis, but one axis is Cartesian axis. This is called semi-log axis. It's not necessary that x-axis will be Cartesian and y will be log. It can be y can also be Cartesian and x can be log. That is also possible. Okay, so that is the difference between the semi-log plots and log plot. Now the question arises, ki, sir, if I plot an equation on semi-log axis and if I plot the equation on log axis, what can you comment about the nature? Of course, the nature will be different because axis has changed. Right? Y is equal to e raised to the power x is having this kind of, I made here, this kind of nature on Cartesian coordinate. But if you plot it on semi-log axis, it will be a straight line. This is important. These are the conclusion for logarithmic graphs. Ki on logarithmic graphs and on Cartesian graphs, if you are plotting the same equation, you are going to get different shapes. Now the question arises, ki, sir, how would we know that an equation is going to look like on the this logarithmic plot? भाई वी हैव अ हैबिट, आपने तो कार्टेशियन कोऑर्डिनेट्स पढ़े हैं बचपन से, आपको कार्टेशियन पे याद है दैट ओके दिस इज द फॉर्मूला ऑफ दिस इक्वेशन, दिस इज द फॉर्मूला ऑफ दिस इक्वेशन, बट what how you are going to know that how the graph looks like if it is plotted on the log plot? Now that is the question. Are you going to plot each and every graph and then find? No. Actually in this case we are lucky that in Bode plots we don't have a variety of graphs, so only one or two graphs are sufficient to understand the nature. Okay, but still I'm giving you a hint that let we want to plot y is equal to x, this is the equation, on log axis. Suppose you want to plot this equation y is equal to x on log axis. Fine. So the question is how it is going to look like, y is equal to x, how it is going to look like if you are plotting this on the log axis, right? How to check? You know that this equation is the equation of a straight line passing through origin, right? On the Cartesian axis, that is a different thing. Suppose we want to plot, y is equal to 1 by x on log axis, है ना? On log axis. Suppose we want to plot, y is equal to e raised to the power x on semi-log axis. Now I have these three questions. You want to plot these three. इसके अलावा आपको और किसी चीज की जरूरत नहीं पड़ेगी. Okay, let us take one more thing. We want to plot y is equal to some constant k, can be 1, 2, 3, can be anything, on log axis. So how it is going to look like? Log axis. Try to think about these four plots. Dekho, if you understand that how the nature of this is going to be on the log axis, everything is fine, right? The only reason why people are not able to understand these Bode plots, one of the reason I feel is the understanding of log plots, logarithmic curves is not clear, right? And the second reason, nobody teaches them about the Bode plot. कई बार बच्चे आते हैं कि सर ये वाला टॉपिक तो कॉलेज में सर ने ऐसे ही भगा दिया था, तो सर को कभी खुद नहीं समझ आया कि Bode प्लॉट कैसे बनते हैं, तो सर ने आपको भी नहीं समझाया, आप भी ऐसे ही आ गए, ठीक है? एंड ये क्या पता नहीं कितने टॉपिक्स ऐसे ही भगा दिए जाते हैं, है ना? दैट इज वाई even I have seen the students of NIT, IIT, they are not clear about this Bode plots. जबकि प्रोसेस कंट्रोल में आपको Bode प्लॉट हार्डली 2 घंटे पढ़ना है, उससे ज्यादा करना ही नहीं है. हाँ, इन सेमेस्टर्स वी हैव अ लॉट ऑफ अदर थिंग्स, other related things. GATE syllabus is, I mean, is just very miniature form of syllabus. आप 6 महीने में वहाँ पे पूरा कोर्स पढ़ते हो, यहाँ आप 6 महीने में पूरा सिलेबस पढ़ डालते हो गेट का, है ना? However, वहाँ सेमेस्टर में 6 महीने कोर्सेज चलते हैं, तो ये भी है कि डेली 1 घंटे या 55 मिनट्स की क्लास होती है. इन वीक यू हैव हार्डली 4 hours लेक्चर्स फॉर 1. सो अगर आवर्स के हिसाब से देखें तो इट इज ऑलमोस्ट सेम. हाँ, वी प्रोवाइड अप्रोक्सीमेटली, आई थिंक दिस प्रोसेस कंट्रोल लेक्चर्स आर गोइंग टू बी 40 to 45 hours. So that is same. It's almost one semester, you can say 3-4 months. Okay, so do one thing, that think about the nature of these graphs on the log axis and this one on the semi-log axis. I hope आपने ये graphs जो है, ये equations you try to plot on these various axes, and let's see what is the nature of these graphs. First of all, of course, no need to take this logarithmic plots and then try to plot. आप करना चाहो कर सकते. If you have logarithmic graph paper, you can plot y is equal to x on that paper, log graph and semi-log graph, and you can see yourself that what is going to be the result. But I'm going to tell you method to check the nature of graph. Method to check the nature of graph on log axis. Suppose you don't have a logarithmic graph paper and still you want to check that how the graph is going to look like on log or semi-log paper, how you are going to do that. So for that I'm going to give you the method. Suppose you want to plot y is equal to x on which axis? Log axis. Write y is equal to x. Fine. You want to plot this on the log axis. Do one thing. Take log on both sides. Don't solve it. Just take log on both sides. Fine. Now consider this as some variable y, consider this as some variable x. What is the equation? Y is equal to x. Means on log graph, the equation y is equal to x will be a straight line. Because y equal to x is the equation of a straight line. Y straight line equation, it will be on the log graph also. Straight line equation. Fine. Very simple to check. Let's take this one. Y is equal to 1 by x. You want to check how it is going to look like on the log graph. Take log on both sides. Log y is equal to log 1 is 0 minus log x. So that is minus log x. Means consider this as some variable y. Consider this as some variable x. So y is equal to minus x. Straight line with slope. Straight line equation. What is the slope? With slope plus 1. Okay. Straight line equation. Straight line equation with slope minus 1. Correct? This is how we can find that what should be the nature of the graph on the log or semi-log plot. Suppose this one, y is equal to e raised to the power x on semi-log axis. If you want to find the nature of an equation on semi-log axis, let's see how we can do this. On the semi-log axis, y is equal to e raised to the power x I have to find. But now in semi-log axis also there can be two cases. Y-axis is logarithmic, x-axis is Cartesian. Y-axis is Cartesian, x-axis is logarithmic. So in that case, there will be various cases. Suppose in this case we have y-axis as the logarithmic axis and x-axis as the Cartesian axis. So how the graph is going to look like? So you are going to take log on both sides. Not both sides, this is semi-log, so only on one side. Y-axis is logarithmic axis, take log, and this one is e raised to the power x. Fine. So can I write this as log of y is equal to e raised to the power x? How it is going to look like on the semi-log axis? What do you think? Or suppose if I take logarithmic on the x-axis, log axis, logarithmic axis will be the x-axis and normal axis will be the y-axis, Cartesian axis. Then what should be the nature? Right. So you can see here in this diagram that if you plot y equal to e raised to the power x, the nature will be a straight line. Right. So you can see here yourself. This is how you can check that what is going to be the nature of a graph on log or semi-log axis without actually plotting them. And आपको Bode plot में इतनी ही जरूरत है. If you understand this much, Bode plot is perfectly alright. Actually, in most, what about this one? Y is equal to constant on log axis, right? So on log axis, y is equal to constant will be a plot. Y is equal to k will be a horizontal line passing through k on log axis. It will not pass through log k, it will pass through k on log axis. That is the graph of y is equal to k on log axis. ठीक है? So इतनी ये थोड़ी सी basic logarithmic axis और Cartesian axis की बात है. Without understanding this, it is difficult to make the proper Bode plots. Okay. So after the understanding of these logarithmic and Cartesian plots, let us now shift to this discussion of Bode plots and let us try to make Bode plots. So the question is कि सर ये Bode plots किसके लिए बनाएंगे? Bode plots are made for all those 7 transfer functions, 7 basic components I told you, for which we found AR and phi. Right, we found the AR and phi for 7 basic transfer functions. For the same basic transfer function, I am going to make the Bode plots also. And just like we made AR and phi for some overall transfer function, we will also make the Bode plots for overall transfer function. Fine. Okay, so right. Let's try to make the first one. The most important one is the Bode plot of a first order system. First order system. Just like the previous cases, we were using the open transfer function. Here also, I'll be using the open transfer function. So GP is equal to KP by tau PS plus 1. For first order system, you have to make Bode plot. So, कैसा बनेगा इसका Bode plot? Before making the Bode plots, let us first understand that in Bode plots, we are not here actually making the exact plot. We are not interested in the exact plot. Nobody is going to ask you what is the value of AR at this particular value of omega from the graph. Of course, you can calculate because you know the numerical function of AR versus omega. But आपको exact graph नहीं plot करना. We have to just make an approximate graph. Idea लगाना कि इसका Bode plot कैसा दिखता है. That's it. Okay. So first order system GP. Do you remember what was the value of AR? AR was equal to Kp divided by root of 1 plus tau p square omega square. Correct? It can also be written as AR by Kp और इस AR by Kp को ही magnitude ratio बोलते हैं MR. AR by Kp is equal to MR is equal to 1 divided by 1 plus tau p square omega square. Right? AR by Kp is equal to MR is equal to 1 divided by root of 1 plus tau p square omega square. Fine. This is how we can differentiate between AR and MR. Correct? So this is magnitude ratio. Now suppose you can see yourself that magnitude ratio is a function of omega, or I can say that magnitude ratio is a function of omega tau. Say in frequency response analysis, tau p is constant, tau p is not going to change. However, omega can change depending upon your input signal. If you change the frequency of your input signal, the output signal frequency will also change. So omega can change, but tau p is constant. So if omega is a variable, omega tau p is also a variable. So whether you make the graph with respect to omega or you make the graph with respect to omega tau, the nature of the graph is not going to change. Right? Because tau p is a constant. ठीक है? तो tau p omega के respect में graph बनाओ या omega के respect में graph बनाओ, doesn't matter. But many times what we see that we make a graph between MR or AR versus omega tau, not only omega. Why? Because tau is there, so omega tau. If tau is not there, for example, suppose what is the amplitude ratio of pure capacitive system? It was Kp by omega. Do you remember? For pure capacitive system, the amplitude ratio was equal to Kp by omega. अब यहाँ tau है ही नहीं, तो you won't plot the Bode plot for pure capacitive system as AR versus omega tau. No, only omega. So if tau is there, then we plot AR versus omega tau. If not, then we'll plot AR versus omega or MR versus omega. So here I'll make first plot between MR versus omega. So I'll use this equation to make that plot. Let us also write the phi. Second plot. What is phi? Tan inverse minus omega tau p. This was the value of phi. Now let us do some calculations here. In this MR calculation, we have two cases. One is LFA, low frequency asymptote. Other one is HFA, high frequency asymptote. I'm writing here. High frequency. What is the meaning of high frequency? Omega is high. High frequency asymptote, and LFA means low frequency asymptote. Right, low frequency asymptote. High frequency asymptote and low frequency asymptote. What is the meaning of low frequency? Omega tau tending to very small value, omega tau tending to 0. Tau or tau p. High frequency means omega tau p is tending to infinity. We don't use actual infinity. Omega tau is very, very high. Hai na? Omega tau is very high. So low frequency asymptote is omega tau p's value is very small. High frequency asymptote is omega tau p value is very large. Actually, in Bode plot, we are only interested in finding the asymptotic values when omega is very small, frequency is very small, and when frequency is very high. जब आपको asymptotic value मिल जाएंगी, then you can add those to make an approximate graph. I'm not going to plot the exact Bode plot, only approximate graph. That is why we are only interested in the asymptotic analysis. Similarly, phi. In phi also we can have two extreme cases. One is omega tau p is tending to 0. The second one is omega tau p is tending to infinity. If omega tau p is tending to 0, then phi is equal to tan inverse 0 minus 0 plus 0 कोई फर्क नहीं पड़ता. Tan inverse 0 becomes equal to 0. Phi will tend to 0. Similarly, when omega tends to infinity, phi becomes tan inverse minus infinity. You know that this is equal to minus pi by 2. So these are the limits of phi for a first order system. But please note that in reality, frequency cannot be zero, because अगर कोई sinusoidal input दे रहे हो, if you are giving some sinusoidal input, it has to be some finite frequency. And also there is no meaning of omega tending to infinite. You cannot have a sinusoidal input with infinite frequency. So these values of phi are not included, they are excluded. You can't have phi is equal to 0 because omega cannot be 0. If it is a sinusoidal wave, it must have some finite value of frequency. So can I say that phi ranges between open bracket means the values are not excluded, right? The value of phi for small frequency it is 0, and for large frequency it is minus pi by 2. And when the omega increases, then it is minus pi by 2, and if omega is very small, phi value is coming out to be 0. This is the range of phi for a first order system. इसको plot के form में मैं बना दूंगा. Now let's talk about this one, low frequency and high frequency asymptote. So I'm going to make a plot here, actually a set of two plots I should say. These two plots together are called Bode plots. The x-axis is omega tau p, y-axis is mr. I'm talking about the magnitude ratio. Mr increases in this direction. Here I have phi is in degrees, and phi becomes more negative in this direction. This is phi is equal to 0. So actually you can make two separate plots also, but because the x-axis is common, and this is, this is log axis, this is log and Cartesian axis. Because this first plot is log plot, the second plot is semi-log plot. So in this plot, both y and x-axis is logarithmic axis. In this plot, y-axis is Cartesian while x-axis is logarithmic. तो कैसे बनाएंगे Cartesian axis? देखो 0, minus 45 degrees, minus 90 degrees, minus 135 degrees. You can see yourself that this is a normal Cartesian axis. While this one is log axis, this one is log axis. I'm not marking it. Okay. Now the question is, you can see here, low frequency asymptote. Means when omega tau p is very small, what is the value of mr? You see yourself, if omega tau p is very small, omega tau p is tending to 0, so omega square tau p square is tending to 0, mr becomes equal to 1. This is the equation, mr is equal to 1. Now mr is equal to 1, when it is plotted on this log graph, what will be the nature? I told you that for y is equal to constant, the nature will be a horizontal line passing through the constant. Similarly, mr is equal to 1, the nature will be a horizontal line passing through a constant. Which constant? This constant. Don't say कि sir ये 0 हो जाएगा because log 1 is 0. No, log 1 is 1 on log axis. So when you plot this graph on log axis, it will be a horizontal line passing through mr is equal to 1. Let's talk about this one. HFA, omega tau p is very, very high. If omega tau p is very, very high, I can say that omega tau p is much greater than 1. In this case, omega tau p is much greater than 1, and therefore mr becomes equal to, please write carefully, omega tau p. Now I have to make a plot between y is equal to 1 by x on a log axis. This is y, this is x, y is equal to 1 by x on the log axis. Now on the log axis, the equation of y is equal to 1 by x is a straight line having slope minus 1. So this line is having a slope is equal to minus 1. Now please note that this is the low frequency asymptote, this is the high frequency asymptote. We know, if you have basic knowledge of graph, asymptotes are not graph. Asymptotes का मतलब graph नहीं होता. Asymptotes are the values the graph is approaching at plus infinity and minus infinity. So what is the actual graph? The actual graph, when it is 0, the actual graph will be at 1. When it is infinity, the actual graph will be here somewhere. Okay, but the actual graph will be something like this. Right? This is the actual Bode plot. These are the asymptote, and this black curve is the actual Bode plot. But actually we are lucky in process control. We don't need to find this or plot this actual Bode plot. For all the future graphs, I will only consider the asymptotes as the actual plot, because we are only doing the approximate analysis. Still I will make the actual Bode plot, but don't worry about the nature. Sir, how I'm going to decide about this gap? Don't worry, that is not your job. Okay, now if I ask you that, okay, these graphs are, these asymptotes are meeting here, Can you tell me what is this value? What is this value? HFA equal to LFA. What is the equation of HFA? HFA equation is high frequency asymptote is MR is equal to 1 and LFA equation is, no, it was LFA, right? HFA equation is 1 by omega tau p and LFA equation is MR is equal to 1. At this value, HFA and LFA is giving you same value, so I can equate them that 1 by omega tau p is equal to 1. So omega tau p is equal to 1 means this value is omega tau p is equal to 1. Right? Now this frequency where the two asymptotes meet is called corner frequency. The frequency, the value of omega at which LFA and HFA meet, the value of omega at which LFA and HFA meet is called corner frequency. Don't ask that, sir, ये इसका significance क्या है? Corner frequency का कोई significance नहीं. It is just a point on the graph where the two asymptotes are intersecting. Nothing to do with the stability. That is crossover frequency. Here, nothing to do with the stability. So omega tau p is equal to 1, and therefore, whenever you want to find corner frequency, you can always find C for corner. Omega C is equal to 1 by tau p. 1 by tau p, you will find the corner frequency. Now, if I ask you that, can you calculate this value? However, it has never been asked in GATE, but still, let us do that calculation. What is that value? Omega tau p is equal to 1. From where you are going to calculate the value? From which equation? This equation? MR is equal to 1? No, because MR is equal to 1 is an approximation of this equation for low frequency. This equation? No, because this is an approximation of this equation for high frequency. So, we will calculate the value of MR from here. Omega tau p is equal to 1. So, this is 1 plus 1, 2, root 2, 1 by root 2. So, this value is 1 by root 2. This can also be asked, possibly, right? This is the graph of Bode plot. What you have to remember actually in the Bode plot, first of all, this is how we plot it. Second thing you have to remember about this nature. Actually, the nature of asymptote. See, for us, for GATE point of view, you can say that asymptotes are the Bode plots. Actually, it is not, but asymptotes, you can see, the actual graph and asymptotes are identical only for smaller values and very high values. In between, there is a significant gap. But still, for our calculation, we are going to say that asymptotes are the plots. Now, let's talk about phi. You can see yourself that the phi value is varying between 0 to minus pi by 2. And it cannot be 0, it cannot be minus pi by 2. What I am going to do? That I am going to make a vertical line here, a horizontal line here. Right. You can see yourself that when the frequencies are small, the value of phi is 0. When frequency are high, the value of phi is minus pi by 2. This is low frequency, this is high frequency. I have to make here 0. So 0. I have to make here minus pi by 2. Minus pi by 2. And then any random kind of graph will do the job. This is the graph of phi. You may ask, sir, why not linear? Why not a straight line? The thing is, this graph, what is the equation? First of all, you see the equation yourself. It's not a linear form. And it is a semi-log axis, right? This is the Cartesian axis, this is not a logarithmic axis. So even if it is a linear graph, it won't be linear on this this semi-log axis. Okay. Now suppose if this is omega tau p, in the graph you can see that this value will be equal to 1. You can put here tan inverse minus 1. So tan inverse minus 1 is 45 degrees minus 45 degrees. So at this value, it will be minus 45 degrees. Only this much you have to remember in the Bode plots. ठीक है, अगर इतना समझ आ रहा है कि कैसे बना, ठीक है, कैसे बनाएंगे Bode plots. Only if this much you understand, then it is very easy to understand, to plot the Bode plots. And that is why I told you that how to understand log-log plots on these graphs. See, log-log plots and how to plot, see, MR is equal to 1 and MR is equal to 1 by x, 1 by omega tau p on log-log and semi-log axis. This is how you can make the first order Bode plot is the most important, and what you have to remember is this shape. Even if you remember this much, for first order system, your job is done, right? Now the question arises, ki, sir, can we make, by using the same ideas, can we make the Bode plots of all other transfer function? Yes. But please note, there are some basic rules which I am telling you that, for example, here AR value was equal to Kp divided by 1 root of 1 plus root of omega tau p square. Okay. omega square tau p square. Now here there was a tau p, so I made a plot between omega and tau p, right? Okay, and why I chose this low frequency asymptote, high frequency asymptote, so that I can simplify this. If this is very high, say, then one can be neglected. If this is very high, this is very small, then this can be neglected, and the values can be simplified. Okay, so by using the same logic, the next Bode plot you will try to make is for PI controller and PD controller. They are quite similar to this. That is why I am giving this one. Don't make Bode plot for second order system. Don't do that. But right now, make the Bode plot for PI controller and PD controller.